Now we're going to use a chi-square test to evaluate if our random number generator on our calculator is actually giving us random numbers. So we would expect if we had a random number generator that was truly random, that we would in the long run get approximately the same number of each digit, 0 through 9. So we're going to follow a procedure here, which you can read and do. I'm not going to actually go through this. Maybe I will. Create a list on your calculator called random number. Do a random seed, put in a number of your choice. So don't put 334 here necessarily. Do random int 0, 9, 150 and store it. This would be control variable to get this little store button to the name of your list, whatever you call it, and it will store all of these numbers into a list on your calculator. Then make a histogram of that list of values. When you make you'll get a dot plot first, then go to menu, plot type, change it to a histogram. And what's nice is you can hover over the bars on the histogram, and each bar then will tell you the number of values in that bar. And the first bar will give you all how many zeros you have, then how many ones, how many twos, and so forth. Those will be your actual counts of in your sample. Now, since we're doing 150 and we are looking to see do we get an equal number, our expected value would be that we would get 15 of each, because that would be an equal number in our sample of 150. So here's our null hypothesis that the digits 0 through 9 generated by random int on the Inspire will all occur in equal proportions over the long run. HA, they do not occur. So HO is really what would give us data consistent with the random number generator being truly random. So I guess we're trying to find out if it's not really. We've got our conditions are all met. Notice that I don't do the 10% condition because I am not sampling without replacement from a finite population. Every time I generate a random number, it's a new independent event, so I do not need the 10% condition here. I'm not like drawing 150 out of a limited population. So I do all my chi-squared stuff. I'm not going to go through all of this. These are the values I got from my test. Yours will obviously be different because you will be generating your own random list. I got a place where I didn't reject the null hypothesis. I would expect most of you probably to get a value of p where value for a p-value where you don't reject the null hypothesis at the 5% level. Some of you will reject the null hypothesis because 5% of the time we'll get an unusual sample and you'll reject the null hypothesis even if it's really true. So, but I want to particularly point out what happens when you fail to reject the null hypothesis here. So I'm going to conclude, since my p-value is greater than alpha, alternatively since my chi-squared value is greater than the critical value I found in the table for 5% alpha, I fail to reject the null hypothesis. By the way, this is a degree of freedom equals 9 because I have 10 categories. I do not have, now listen to this, I do not have convincing evidence that the digits generated by random int on my calculator are not equally distributed. So I don't have evidence that they're not equally distributed. Okay, that's kind of crazy. So do I have evidence that they are equally distributed? Well, no, because I can't accept the null hypothesis. But I can say the data appear, oh, that should be singular, the data appear to be consistent with what I would expect from a random number generator. Now this helps explain why biology treats a chi-square test conclusion differently than we do often, because that really doesn't help me a lot to say I don't have convincing evidence that they're not equally distributed. Wouldn't it be nice to just to say I have evidence they are equally distributed? I can't technically say that, but I can say that they are consistent with what I would expect. So here's what happens in biology a lot. In biology, the null hypothesis is usually that the data is consistent with some biological theory. Maybe it's a theory of genetics or something along those lines. Got to wait a little bit for Mrs. Tolles to give her announcement. So a high p-value, which means that we don't reject the null hypothesis, indicates that the data is consistent with the theory. We can't prove the theory is true using this statistical method, but we can say that our data doesn't contradict the theory. So that's probably what's happening in AP Biology with the chi-square test. Unfortunately, a lot of times what we want to prove is we would really like to know if our null hypothesis is true. So the high p-value is actually what we want to see. Even though we can't technically prove it's true, we can say that the data seems to be consistent with our null hypothesis value.